Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 3.9. Related rates.
Lesson 2. The helicopter and the car. So let's go ahead and look at our second example on the next page. You'll notice this example, as we start to read through it, looks very different from the one we did before, but it's still a related rates problem, and so we can still break the problem apart with exactly the same steps and stages that we did in the last problem. One thing I want to mention as we go through the rest of the examples in this section is that it's very important for you to actually pause the video and try to fill in some of these steps yourself. That's the only way that you can learn how to do these problems, is to practice pulling the information from the problem and the stuff that's pertinent for each of the different steps here. So take advantage of this video format because you can pause the tape, think about the problem yourself, and then we can always go through it together. If you get stuck, that's normal. These are tough problems. Okay, let's read this one. You are traveling due east at 60 miles per hour along a straight highway. So you're actually in a car like this, and here's the highway, and you are traveling towards the east. A low-flying helicopter travels due north at 80 miles per hour. So here's a helicopter that is going due north, and it's going at a constant 80 miles per hour. You're going at a constant 60 miles per hour. Find the rate the distance between you and the helicopter is changing. So the distance from you to the helicopter at the instant when you are 3 miles east of the point where the helicopter passed over you. So at some point you were right here, and that's the moment when the helicopter passes over you, when you're right here. And we want to know how fast is the distance between the two of you changing at the moment that you are 3 miles down the road. Okay. I want to mention also that this drawing is not to scale, and generally we need a sketch. If the sketch isn't provided for you, you can draw your own sketch. And it doesn't necessarily have to be to scale, it just has to be accurate enough for us to be able to write down the relating equation and all of the other information that's pertinent to the problem. So just keep that in mind, that this is not terribly to scale. So let me just sort of recap what this picture looks like. At some moment in time, you and the helicopter are both at this point, and then you drive off at 60 miles per hour in this direction, and the helicopter, its distance is kind of shrunk here to fit onto the page. It's going off in this direction at 80 miles per hour. Okay, let's try to identify the quantities that vary, and specifically we want the quantities that are discussed in the problem. So take a moment if you can and think about it. In this case, there are actually 3 quantities that vary. Pause the video and see if you can decide what those quantities are, and if you do, label each of those quantities with a letter, a variable name, and write down that each of them is a function of time. Okay, so let's try this together. It can be a little bit tricky when you first start doing these things. You notice that some things are changing. For example, your distance from this point where the two of you were right together, the helicopter and you were right over the same point, your distance from that point, I'm going to call it the point P, is changing. So x, let's call it x, will be your distance from point P. That is a quantity that is changing, and so if I want to, I could write x equals some function of time. I'm not going to write down specifically what function of time. Also, the helicopter is moving in this direction, so its distance from the point P is also varying, changing. So I'm going to call its distance from the point P y. So y is some function of time. And if you use different letters or something like that, there's no problem with that. But you may want to change them to this just for the rest of the problem. Now there's actually another quantity that's changing that's described in the problem, and that has to do with the rate that they're asking us to find. They say find the rate the distance between you and the helicopter is changing. So let's also label that in the picture, and that line is not really drawn. It's the distance between you and the helicopter. So I'm going to go ahead and draw another line in here, and whatever that distance is, we're really going to be looking for the rate that that distance is changing. So at any moment in time, it's equal to something. Maybe I'll call that z. So z, you can see that as the two of you go off in these directions, z is going to be changing. So z is also a function of time. Okay, next thing we want to do is write down the rate that we know and the rate that we want. And in this case, I'll give you a little hint. There are actually two rates of change that you know, and there's one rate of change that you are asked to find. So two rates are given. One you want to find. Try to write the rates that you know down in terms of numbers, but also in terms of symbols. And then try to write down the rate that you want in terms of symbols. So pause the video and try to extract that information from the stuff that's discussed up here in the problem. And if you get stuck, start the camera again, the video again, and we'll go ahead and do it together. Okay, well, what rates do I know? We do know some rates of change. We're told that you are traveling due east at 60 miles per hour. And remember, mph really is a rate of change. It's miles per hour. So it's the rate that your distance is changing in time. So we do know that you are moving in this direction at 60 mph. That means that your distance from point P, which we called x, is changing at the rate of 60 miles per hour. So the rate that we know, or one of the rates that we know, is x prime of t, or you could write it as we usually do, dx dt. The rate that your distance x from the point P is changing in time is 60 miles per hour. And instead of writing mph, I'll write it in a more mathematical way, miles over hours. Now, I left it as a positive 60 miles per hour. Does that make sense? And to answer that question, we just look at the function x and we decide, is it an increasing function or is it a decreasing function? As time goes on, is x getting bigger or is it getting smaller? You notice that as time goes on, you're moving in this direction, and so x is getting larger. If you thought of drawing an x versus t graph, it would look something like this. What does that mean? It means that if I were to draw the tangent line to this graph at any point, it would have a positive slope. And remember, the slope of the tangent line to the graph is the same as the derivative. So dx dt should be a positive 60 miles per hour. Not a negative. That would mean that x was a decreasing function in time. It would mean that you were going towards P instead of away from P. Okay, we actually do know another rate. So I'm going to kind of put a line here because there are two rates of change that we are given in this case. And then we'll do the rate you want underneath this. The other rate of change that we know is the helicopter. We're told that it is traveling due north at 80 miles per hour. So that's also a rate of change. What's it the rate of change of in terms of what we've labeled in our picture? Well, that's the rate that the helicopter is moving away from point P. So it's the rate that its distance, which we called y, is changing in time. So it's really the derivative y prime of t. It's the rate that y is changing in time. So you could write y prime of t, or more traditionally we write dy dt, and that would be equal to 80 miles per hour. Okay, and is it okay to write a positive 80 miles per hour? It is, because y is going to be increasing as the situation moves along. Since the helicopter is moving in this direction, y is an increasing function, just like x was an increasing function. So the slope of its tangent line will be positive, and the slope of the tangent line is the same thing as dy dt. So that should be a positive 80 miles per hour. Well, what rate do I want? In other words, what rate am I asked to find? And hopefully you looked through and saw that you are asked to find the rate, the distance between you, so find the rate that the distance between you and the helicopter is changing at some certain instant, at the instant when you are 3 miles east of the point where the helicopter passed over you. In other words, east of the point P. So the rate that I want is how fast this distance z is changing. So the rate that I want is dz dt. And I want that at a certain instant in time. And I'm going to put that in parentheses because we won't use that until the very end. I want it at the instant when, and let's see, we want it at the instant, it says find the rate, the distance between you and the helicopter is changing at the instant when you are 3 miles east of P. So you are right here, and that means we want it at the instant when your distance from P is 3 miles. In other words, when x is 3 miles, since that measures your distance. So when x is equal to 3 miles. We won't use that till the very end of the problem because during the course of the problem, x is a function of time and is changing. And this is just its value at the moment when we want to find dz dt. Okay, let's go ahead and think about step 3, the relating equation. And remember, it's going to relate the quantities that we found in step 1. So you want an equation that relates x, y, and z together. And can you think of an equation that relates x, y, and z together? Take a moment, pause the video, try to write down the relating equation, and if you get stuck, just start the video up again and we'll go through it together. Okay, well, remember that the way the problem was described, you are going due east and the helicopter is going due north. And so what's true about the angle here? This has to be a perfect right angle. And that means that we have actually a right triangle in our picture. So I'm going to kind of highlight the triangle in green, where the sides of the triangle are y, x, and the hypotenuse we labeled z. Well, since it's a right triangle, what theorem applies? The Pythagorean theorem from geometry applies. And so I know that x squared plus y squared has got to be equal to z squared. X and y are the sides of the right triangle, and z is the hypotenuse. So that's just the Pythagorean theorem from geometry. And yeah, you have to kind of recognize that it's a right triangle and think, well, what could relate these 3 sides together? Oh yeah, I remember the Pythagorean theorem relates the sides of a right triangle together. I'm also going to write these, I wrote it in this sort of short notation where I've suppressed the fact that x, y, and z are each individually functions of time, but for the next step, it's nice to actually write that out and remember that x is really some function of time. So I'm going to write x of t is quantity squared plus, same thing with y, y of t quantity squared has got to be equal to z of t, that quantity squared. Okay? Now I want you to think about the fact that the left side of this relating equation equals the right side. Somehow we have to get from this relating equation to one that involves the things we're given and the thing that we're trying to find. In other words, we want to get from something involving x, y, and z to something involving dx dt, dy dt, the rates that we know, and dz dt, the rate that we're looking for. And the only way to do that is to differentiate. And because we want dx dt, dy dt, and dz dt to appear in the final equation, we need to differentiate with respect to t, with respect to time on both sides. So take this equation and go ahead and try to, I'm going to write that step for you, try to differentiate this with respect to time. And I'm going to kind of spread everything out because we're going to need room in the next line. And what we're saying is simply that the left side of this equation equals the right side. So if we differentiate the left side with respect to time, that should equal what we get on the right side if we differentiate with respect to time. So go ahead and try to find the derivative. And here, finding the derivatives is very similar to the process that we did in the last example. So pause the video, try this problem, and see if you can go ahead and differentiate with respect to time on both sides. Okay, so now let's go ahead and try this together. When I take the derivative of this with respect to time, notice that there is an inner function and an outer function. So for this first term, I have an inner function of x of t, and the outer function would be the t squared function. Because it's a composition with an inner and an outer function, in order to find the derivative, what rule do I have to use? I have to use the chain rule. So let's go ahead and try to use the chain rule there. Remember, chain rule says derivative of the outer evaluated at the inner times the derivative of the inner. So I start by doing the derivative of the outer. Well, that means I'm going to pull down the 2, and if I do it with empty parentheses, everything's going to be to the first power. So that's the derivative of the outer. I have to evaluate it at the inner, and the inner function is x of t. Okay? But by the chain rule, I have to multiply by the derivative of the inner function. So I have to multiply by the derivative of x of t. But what's the derivative of x of t? Well, I don't know what function of t this is, so the best I can do is just write x prime of t. That would be the derivative of the inner. So we have derivative of the outer evaluated at the original inner times derivative of the inner. It's just the chain rule. The same exact thing would work for the derivative of y of t squared. I again need the chain rule because I have an inner and an outer function. So let me put this plus sign that's between these two terms. And when I take the derivative of this term, I do the same thing. Take derivative of the outer. It would actually be exactly the same derivative because it's the same outer function. I evaluate it at the inner. The inner is now y of t. And I multiply by derivative of the inner. I don't know what function of t y is, so the best I can do is just write times y prime of t. So now let's look at the right-hand side of our equation and see if we can do that derivative. Same exact idea. I have to use the chain rule here. So I'll do the derivative of the outer, same exact outer function, so it's 2 times whatever I plug in to the first, and the thing I'm plugging in is my inner function. Well, in this case, my inner function is z of t. And then by the chain rule, I have to remember to multiply by derivative of the inner, and derivative of z of t is just z prime of t. So now we've taken all of our derivatives. The next thing I'm going to do is just to try to clean this up. So just as we did in the last example, I'm going to go ahead and instead of writing this as x of t, remember that that's the same thing as x, just expressing the fact that x is changing in time. I'm going to suppress that of t at this point. The only reason I wanted to put it in up here was so that when I differentiated, I knew that I needed the chain rule, that I had an inner function of t and an outer function of t. So I'll suppress the of t part and just write x. It's x to the first power, so that's just x. The x prime of t, remember, is just our alternate notation for dx dt. So let me write the x prime of t as dx dt again. And let's see, so then I'm going to have a plus I have a 2, and I'll do the same thing with y of t, just write that as y, and y prime of t, same thing as dy dt. And on the right side of the equation, I would have 2 times z of t is the same as z, and then I'll multiply that by dz dt. So now we've gone from our relating equation that related the quantities that we see in the problem together, x squared plus y squared equals z squared, and by differentiating with respect to time on both sides, we now have an equation that involves the quantity that we want. Remember, what we're looking for is dz dt, and I can see that that's in here, and it involves quantities we know, such as dx dt and dy dt. Okay, well, let's go to the next page where we're going to do step 5. And in this particular problem, step 5 is a little tricky. We have to do kind of an extra step in order to plug everything in. So I'll show you what I mean by that. But before we do that, let me go ahead and just rewrite what we had on the last page. It was 2x dx dt plus 2y dy dt is equal to 2z dz dt, and right away I can see that there's a common factor of 2 on both sides of the equation. Let me divide through by 2 and just get rid of that. So I'm going to write it as x dx dt plus y dy dt is equal to z dz dt. And remember that what we were looking for on the previous page, the rate that we wanted, was dz dt. So let's go ahead and solve for the rate that we want, and all we mean by solving for the rate that we want is isolating the dz dt on one side of the equation. So I'm going to go ahead and do that by dividing both sides by z. I'm also going to turn both sides of the equation around, so I'm moving the left side of the equation to the right and the right side of the equation to the left. So let me go ahead and just move this over. So I'm going to write dz dt, and then the other side of the equation I'm going to divide everything by z. So it will be equal to x dx dt plus y dy dt, all divided by z. So I divided both sides by z, and I also flipped both sides of the equation, interchanged both sides. Okay, well, remember that we did in our last example was we solved for the rate we wanted. Actually, in the last example, it was already isolated. And then just plug in the stuff you know. Okay, well, if I say, yeah, I want dz dt, remember that we wanted dz dt at a particular moment in time. I'm going to go back to the previous page just for a moment so that we can check that out. The rate we wanted was dz dt, and we wanted it at the instant that x was equal to 3 miles. So you're moving in your car along here, x is different values. We want to know how fast is the distance between you and the helicopter changing at the instant in time that x is equal to 3 miles. So we want it at that instant in time. So let me just translate that over to this page. We said dz dt, and we want it at the moment that x is equal to 3 miles. Not at any other moment, and dz dt will be a different value at different moments. Okay, so let's go ahead and see what we know and can plug in. Well, x, I want it at the moment that x is 3 miles. So I'm going to replace x with 3 miles. That looks fine. I'm going to multiply that by dx dt, and you might remember from step 2 on the previous page that dx dt was a value that we knew. Let me see what I had for that. Dx dt was the 60 miles per hour. So we do know this value. We know that it is equal to, let me move these parentheses over just a little bit so I have more room. So I'm going to replace dx dt with 60 miles per hour. And what else do I have here? I have a plus y, And dy dt, that was the other speed that we had. That was the speed of the helicopter. That was 80 miles per hour. So if you go back to step 2 on the previous page, you'll see that dy dt was another rate that we knew, 80 miles per hour. Y is not given. And that's why I said this one is a little bit trickier. And z is not given either. We're told we want dz dt at the moment that x is equal to 3 miles. And we're really not told what y and z are at that instant in time. But it turns out that these two things are things that we can figure out. So if I know that we want it at the moment that x is 3, that's going to determine what y is and what z is. So here's x, that's equal to 3 miles. Y we don't know, but we want y at that same instant in time, and z we don't know, but we want z at that same instant in time. Well, how are we going to figure out these two things? Let's kind of do that on the side. I'm going to do it sort of in a little sort of piece of scratch work here over on the side. So we know that x, we want that dz dt at the moment that x is exactly equal to 3 miles. And we also know that you're speeding along in this direction at 60 miles per hour. And since you're going at a constant rate, we could go ahead and say that your distance at any time as you're moving along towards the east is equal to your rate times your time. And what I'm going to do is try to figure out, well, how long does it take me to go those 3 miles? If I could figure out the time that it takes me to go 3 miles, I could apply that to this side because I know that the helicopter's moving in this direction at the fixed speed of 80 miles per hour. So let me show you what I mean there. We want your distance to come out to be 3 miles when your rate we know is a constant 60 miles per hour. And if you want to, you can put the units on here, 3 miles, 60 miles per hour. And what I'm asking is how long does it take you to go those 3 miles if you're driving 60 miles per hour? Well, that's easy enough. I just solved this for t by dividing both sides by 60. So I will get 3 miles over 60 miles per hour. If I invert and multiply the units, it would be times hours over miles. And you notice that this would reduce to, I guess, 1 over 20. So I get 1 over 20. The miles drop out, and I get 1/20th of an hour. So that's how long it takes me to drive this 3 miles if I'm going 60 miles per hour, a 20th of an hour. Which I guess is, the same as 3 minutes. Is that right? Yeah, 3 minutes. So that's how long it takes me. So at that same moment in time that I've driven 3 miles, which takes 1/20th of an hour, the helicopter has moved a certain distance. Well, how far has the helicopter moved? If I want to know what's y when the time that's elapsed is 1/20th of an hour, all I need to know is how fast the helicopter is going, and to use this distance equals rate times time formula again for y. So the distance that the helicopter has gone, I'm just going to call y. The rate that the helicopter goes is a constant 80 miles per hour. And the time that it's going to travel is the same time that it takes the car to go 3 miles, so that's 1/20th of an hour. And if I simplify all of that, what will I end up with? I guess I'll end up with 4 miles. You can see that my picture is really not to scale because y, at the instant that x is 3 miles, y is actually equal to 4 miles, and it looks shorter on my picture. But the diagram is really just to help me get the relating equation, so that's all right. So I have figured out one of these things here. I'm going to go ahead and erase the question mark for the y. I've figured out what y is. At the instant that x is 3 miles, y turns out to be 4 miles. So I'm going to put a 4 miles in here. The only other thing that I don't have on the right-hand side that's preventing me from finding dz dt is the z value. I want you to pause the video for a moment and see if you can figure out when x is 3, and y is 4, can you find what z is equal to? So pause for a moment. We don't know how fast z is changing, but there's another way to figure out z. So work on that for a moment. If you get stuck, just restart the video and we'll go through it. Okay, let's go ahead and go through that together then. We found what y was. We did that here. Let's see if we can also figure out what z is equal to at the moment that x is equal to 3. Well, if x equals 3 and y equals 4, can we figure out what z is? Yes, we can, and we could do it without worrying about times or anything like that. We can just do it from the Pythagorean Theorem. This is a right triangle. This side's 3, this side's 4, and we're trying to find the hypotenuse. And we know that x squared plus y squared is equal to z squared. That was our original relating equation. And I'll just plug these in. I want x to be 3, so 3 squared. And we found out that at that moment in time y is 4, plus 4 squared has to equal z squared. So it looks like I get 9 plus 16 would be 25 for z squared. That means z is either plus or minus 5. We wouldn't want z, which is a distance in our physical problem, to be a negative 5, so I'm going to choose the positive square root just because of the physical problem that z represents. And so z would be equal to 5 miles. And if you want to, you can keep the units in here. You'll get 25 miles squared, and when you take the square root on both sides, you'll get 5 miles, and the units there are miles. So now we've also figured out what this question mark is. Let's see if I can get my finger wet. I have a sponge to wet down my finger. We know what the z value is, and I can say that when x equals 3 miles, it turns out that z equals 5 miles. So these things we were basically given, the x, the dx dt, and the dy dt. The other things we had to do a little bit of work to find out, but they were all things that we could compute. Okay, so that's great. Now let's go ahead and just try to simplify this whole expression. I think I multiplied this stuff out. I did it actually in 2 steps so that I kind of keep track of the units. 3 times 60 gave me 180. And you notice the units there are really miles squared because I have miles times miles per hour. And then I add on 4 times 80, so that's going to be 320. And again, it's miles squared per hour. And down below, I have the 5 miles. So in the numerator, when I add those two things together, 320 and 180 gives me 500 miles squared per hour. And I'm dividing by 5 miles, and so it looks like I'm going to get 100, and the miles, one of these miles in the top cancels with the miles in the denominator, so kind of as a rough check, if we carry the units all the way through, we can make sure that those units make sense for the type of rate that we're looking at. So what we end up with as an answer is that dz dt, that's the rate that z is changing. So it's the rate the distance between you and the helicopter is changing. dz dt at the moment that you are 3 miles down the road turns out to be 100 miles per hour. And let's just ask a couple questions in our head just to be sure that this kind of checks out and makes sense as an answer. Remember that your distance from this point that we called P is increasing. Y, the distance of the helicopter from the point P, is increasing. And what we're saying is that dz dt is equal to 100 miles per hour. Because it's a positive value, that would imply that z is increasing. So this is positive. Derivative means that z is increasing. And does that make sense? Would z be getting larger? If x is getting larger and y is getting larger, this whole right triangle is getting larger, and so yeah, it makes sense that the distance between you and the helicopter should be increasing. And that means again that If you thought of it as a t versus z curve, you've got to have a curve that's going up as you go to the right. Z is an increasing function. And if you thought about the tangent line to such a curve, the tangent line has to be slanted upwards, meaning the slope of the tangent line, which is the same thing as dz dt, the derivative, should be something that is positive rather than negative. And that's what we got here. Also, do the units make sense? I have miles per hour as my final units. Well, z is a distance, and dz dt is supposed to be the rate that distance is changing per unit time. And that is what we have. Miles is a unit of distance, and hours are a unit of time. So my distance from the helicopter is changing at the rate of 100 miles per hour, per 1 hour. Okay, great. Let's go ahead and we'll look at the next page and the next example.